Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Module 048, Relaxation Oscillators, the types, the principles, and the application. Please follow me in the Engineering Lecture Series by subscribing to my YouTube channel at https://youtube.com/@ndinechimichaelc. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can listen to related lectures on oscillations and feedback oscillations using the two links provided. You can also visit Ebony Educational Consult website at www.ebonyeducationalconsult.com for more engineering lectures. Like we introduced the topic, our topic today is relaxation oscillators. So what class of oscillators are known as relaxation oscillators? We say that they are those oscillators that do not use feedback loop for their operations. These classes of oscillators use an RC timing circuit and a device that changes states to generate a periodic waveform. In other words, we are not talking of oscillators that produce only sinusoidal waveforms. Under these relaxation oscillators, we will learn about circuits that are used to produce non-sinusoidal waveforms, and we will be using the 555 timer to illustrate how these classes of oscillators work. Now, let's talk about the 555 timer as an oscillator. The 555 timer is an 8-pin dual inline integrated circuit that's used for many applications. When we say 8-pin dual inline, we mean that you have the chip and 4 pins on one side, 4 pins on the other side. So the 8-pin dual inline integrated circuit. As we go on, you will see how the numbers, the numbering are done so that you know by holding it which one is pin 1, which one is pin 2, and so on. This 555 timer can be configured as an astable or a bistable multi-vibrator. The astable form is sometimes referred to as free-running multi-vibrator. As we go on, we will see why it is also regarded as free-running. It can also be used as a voltage-controlled oscillator, VCO. The 555 timer consists basically of two comparators, a flip-flop, in most cases SR flip-flop, a discharge transistor, and a resistive voltage divider. The internal working diagram of a 555 timer integrated circuit is as shown in Fig 1. So if you look at the figure here, you see that inside the chip, this is what you see. You will see two comparators, the upper and the lower comparator. You will see a discharge transistor. You will now see the SR flip-flop. You will see the output buffer. These are the major 5 components you see inside the 555 timer. Of course, you have the resistors, which are very common. So the resistors you can see are providing the divider circuit. If you look at the lines, you see numbers put in brackets. They represent the pin numbers of the 555 timer. So you see pin 1 is the ground, pin 2 is the trigger, pin 3 is the output, pin 4 is the reset, pin 5 is the control voltage, pin 6 is the threshold point, pin 7 is the discharge pin, while pin 8 is the VCC, that is the supply voltage. So let's see how it works. This 555 timer that has that internal working diagram can be connected to act as an astable multi-vibrator or a free running relaxation oscillator. When it is connected as an astable multi-vibrator, it is essentially a square wave generator when connected as shown in Fig 2. Here, in that Fig 2, we will see shortly, the threshold input is tied to the trigger input. The external components R1, R2, and C external form the timing circuit that sets the frequency of oscillation. The 0.01 microfarad capacitor, which is connected to the control pin or control input, is strictly for decoupling and has no effect on the operations. By now, we assume that you know what decoupling means. When you connect a capacitor as a decoupling, it helps you to remove the unwanted signals, those ripples that may affect your system. It helps you to ground them. So you call it decoupling capacitors. So now you see what we are talking about. The 555 timer, to work as an astable multi-vibrator, you have to tie pin 6, the threshold pin, to the trigger pin. Then you have the R1 and R2, which we say is the resistive voltage divider circuit. Now, if you look at pin 4, reset, you see that I deliberately used a small round circle, which I used red to indicate, to show that at that point, it is the negative signal or the low going signal that activates that pin. Of course, you see the VCC connected to pin 8, the coupling capacitor, and so on. Now, what happens is that when the power is switched on, the external capacitor, known as the C external, is uncharged, and this is connected to the trigger pin. Let's see that very well. So when it is connected, when you switch the power on, the VCC, which is the the supply, is switched on. The C external the capacitor you see, which is external to the circuit, is uncharged, and thus the trigger voltage, that is pin 2, is at 0 volts. This causes the output of the lower comparator to be high. From our previous circuit, you saw the lower comparator. This forces the output of the lower comparator to be high and the output of the upper comparator to be low. Maybe we go back to that, but we assume that you've seen the diagram. Again, when this happens, as the external capacitor is being charged through R1 and R2, which is the divider circuit as shown in Fig 3. Let's see. As shown in Fig 3, and when this capacitor charges to 1/3 value of the VCC, the lower comparator switches to its low output state. When the comparator voltage reaches this 2/3 of the VCC, the upper comparator switches to its high output state. Let us get it again by looking at this diagram. When the VCC is switched on, if you follow the green arrow coming down, at the point it is switched on, the trigger, which is pin 2, is at 0 volts because the capacitor is completely discharged. So no voltage passes to get to pin 2, which is the trigger. That is why I used the red line to show the connection to pin 2. That red line is only connected to pin 2 and the positive sign of the upper comparator. Now, in our subsequent lectures, when we look at operational amplifiers, you see that the positive sign is called the non-inverting input. But pin 2 is to the inverting input of the lower comparator, while it is tied to the non-inverting input of the upper comparator. So we say when you power on, C external is at 0 volts. Then as it begins to charge, when it gets to 1/3 of VCC, the lower comparator switches to its low output, and when the comparator voltage increases and reaches to 1/3 of the VCC, the upper comparator switches to its high output value. What helps to do that is as a result of the difference between R1 and R2, which divides the voltage. Now, when the output of the lower comparator becomes low, forces the output of the flip-flop and the base, the output of the flip-flop Q and the base of the discharging capacitor QD to go low, thereby keeping the transistor in the off state. When that happens, the result of the flip-flop causes the QD to go high. When it goes high, the output turns the capacitor on. This sequence creates a discharge path for the capacitor through R2 and the transistor as indicated using the small green arrows. The capacitor begins to discharge because it has charged, and when it begins to discharge and this sequence happens, then it starts discharging the content. At the point where this capacitor discharges to 1/3 VCC, the lower capacitor switches high, setting the flip-flop, which makes the base of Q4, which is QD, the transistor, to turn off the transistor. Then another charging cycle begins, and the entire process repeats itself. So as that is happening, if you look at down where we have the waveform like sawtooth that I put in orange and purple, you see that at 1/3 VCC, the lower comparator starts charging and the signal continues to go up. When it gets to 2/3 VCC, it turns on the upper one, which I represented as 2. Then as that upper one, the capacitor continues to discharge and the signal continues to fall down, or the voltage level continues to fall down, which is the purple color. It gets back to 1 and the process repeats again. So the output of the RS flip-flop, which is normally 2 outputs, one Q bar. So the output will drop from 1, then goes up. That is the pulse form we are showing to the right under the output buffer. So you see that what you are giving out at output will be a rectangular waveform which goes up from state 1 to state 2, remains there until a point it gets state comparator 1, switches on again, it goes off. So you have on, off output, which is in form of a rectangular waveform. So when this happens, you will now see that you have output between the time the voltage is 1/3 of VCC and when it is 2/3 of the VCC. The two comparators work at different times, thereby giving different outputs that shows the top edge and bottom edge of your rectangular waveform, or it could be a square waveform depending on the value and the time constant you have chosen. The result of the output is a rectangular waveform whose duty cycle depends on the values of R1 and R2. The frequency of operation is given as FR equals 1.44 over R1 plus 2 R2, or into value of external capacitor. By selecting suitable R1 and R2, the duty cycle of the output can be adjusted as duty cycle equals ratio of R1 plus R2 over R1 plus 2R2 times 100%. We take that as the duty cycle. So this 555 timer can also be connected as a voltage controlled oscillator. So that can be done by using some form of external connections for the unstable we have seen above. The exception is that the variable control voltage is applied to the control input, which is pin 5, When this is done, the control voltage will be as shown in Fig 5, which changes threshold from values of 1 over 3 VCC and 2 over 3 VCC for internal comparators. With the control voltage, the upper value, which is V control, and the lower value is 1 over V control. That is the control voltage you are applying. When the control voltage is varied, the output frequency also varies. An increase in the V control increases the charging and the discharging time of the external capacitor and causes the frequency to decrease. A decrease in the V control decreases the charging and the discharging time of the capacitor and causes the frequency to increase. This is what we are saying, that if you reconfigure the 555 timer, it can give you a voltage control oscillator. Now, this is done by applying a control voltage to P5. Whatever voltage you want to use to control the oscillation, you apply it to P5. When you apply it to P5, then it sets the VCC to start operation, but the control voltage you are applying when the upper comparator is at half the V control, whatever control you are putting, when it is 50% of it, changes state. And when it is 100% of it, it changes another state. And we say that as you increase this V control, it affects the charging and discharging rate of this external capacitor. So the higher the V control, the lower the frequency. The lower the V control, the higher the frequency. So this is what we're saying. We've seen this type of plots when we talked of being connected as an unstable multi-vibrator. But when you are now applying to the control P5, you see that it becomes, instead of acting between 1/3 and 2/3 of the supply voltage VCC, under the VCO, that is as a voltage control oscillator, it acts when the value is the value of the control voltage you are applying and when it is 50% value of the control voltage you are applying. So when you do that, you still see a similar going up, which we represented with orange, going down, which we represented with purple. So it will continue to go that. And when that is happening, what you will be seeing is that when it is going up, it gives you the leading edge of the pulse. It follows a curve. So at the point where the curve terminates and starts going down, it gives you the trailing edge of the pulse. So when it gets to half V control, it continues to rise again. Your output remains constant until it gets up to the value of V control. When it gets to that place, then the output continues to decrease, and that gives you the trailing edge of the pulse. So it continues like that to give you a rectangular pulse depending on the value of the control voltage you are using. That will give you the duration tau of the pulse you are getting. These multi-vibrators we have looked at, said it can come as an unstable multi-vibrators. It can come as a monostable multi-vibrators. But it is very important that we know each time we are talking of multi-vibrators and we are specifying a stable or monostable, that we know exactly what we mean. For the unstable multi-vibrators, we are planning to use it to do square wave generator, which is used in timing circuits, waveform generators, and digital clocks. These unstable multi-vibrators can also be used in pulse generation, where it produces clock pulses for digital circuits and microcontrollers. When you are starting to do your designs, you see that you always use clock pulses to synchronize the operation. So it is these unstable multi-vibrators or the free-running oscillator that you make use of. We also use it for flashing of lights, LED blinkers, which you see in toys. Also for tone generation used in alarms, sirens, and audio oscillators. Frequency modulation in communication circuits for generating carrier signals. You know that when you are modulating your signal, you have your signal you want to modulate. You use a carrier signal to modulate it. So you generate such carrier signals using multi-vibrators, more especially the unstable. Have another form of multi-vibrator which you call the monostable multi-vibrator, which is used when you want to get a timer circuit, produces a single output pulse of defined duration. So if you want to introduce a delay in a digital circuit, you use these monostable multi-vibrators because it will give you just one shot. The duration will determine the delay you want to introduce. It can also be used for pulse stretching or shaping, which converts a noisy or a narrow pulse into a clean, wider one. Used for switch debouncing. In our subsequent lectures, we'll be able to talk more about switch debouncing. But by this debouncing, it helps to remove unwanted bounces from mechanical switches. Also, used as frequency dividers. By using a trigger input, it can divide, frequencies. And more especially, these monostable multi-vibrators are applied in radar and communication systems for pulse width control and synchronization. Please follow me and subscribe to the channel so that you will get notifications when we'll be, talking on another form of multivibrators, which is known as bistable multivibrator. In that lecture, we'll be able to differentiate properly between a stable, monostable, and bistable multivibrator circuits. So you see the difference between them. Thank you for listening. Please share, comment, and subscribe. Thank you.